In this video, we're going to learn a new integration method that will allow you to solve a specific class of integrals that can't be solved by taking simple antiderivatives or by doing a u substitution. And this method is called integration by parts. And the specific class of integrals that it allows you to solve has this form. It's some function times another function as your integrand. And of course, u substitution allows you to solve some functions of this form. For example, the integral of x times e to the x squared dx. You know, if you let u equal x squared, then if you took the derivative of that with respect to x, you would get that du is equal to 2x dx. Dividing both sides of this by 2, you see that 1/2 du is equal to x dx. Well, here in our integral, we have x dx that we could substitute for 1/2 du, and we have e to the x squared. X squared, of course, is u. So note that this whole thing could be converted into 1/2 e to the u du. Note that we went from having two functions of x to a single function of u, and we know how to take antiderivatives of single functions. So this is a case where you would be able to use u substitution, but there are many cases where you cannot. So I can show one example. If you had the integral of x times cosine of 5x with respect to x, u substitution will not help you here. You can't do u equals x. That's not a substitution. That gets you anywhere. But what if you did u equals cosine of 5x? Well, if we took the derivative of this with respect to x, we would get -5 sine of 5x dx. And this isn't helpful. We don't have a sine of 5x here that we can substitute that with. We have an x, we have a cosine of x. We can do this and we'll just get, we'd have to solve for x in terms of u, and it's not going to get you anywhere. You don't want to do any of this. What you want to do is use integration by parts. And if you didn't know that, you would have to come up with it on your own. You'd have to come up with some formula on your own that takes this form where you have some function of x times some other function of x as your integrand. And then you would want to develop an equation that lets you solve for an integral of this type with this as your integrand. And so we're going to do that. We're going to actually derive the integration by parts formula. And so here, if we have f of x times g of x, this is a general thing. We don't know exactly what it equals, but we can make an equation if we took the derivative with respect to x of this product here. Because we know we can use the product rule, and this would give us f prime of x times g of x plus just f of x, right, times g prime of x. Now, like this, as it sits, this isn't helpful. We have a bunch of derivatives and just regular functions here, and we need integrals. That's what our target is something that shows the integral of one function of x times another function of x, and coming up with some equation that allows us to solve that. Luckily, using algebra, we can come up with something just like what we need, simply by taking the integral of both sides with respect to x. So here we want to take the integral of this entire thing with respect to x on the right side. Okay, note that here we have a situation where the fundamental theorem of calculus, I don't know if it's part 1 or part 2, but one of them will help us out, because one of those says that if you took the integral of a derivative, you will sort of just one cancels out the other. These are inverse functions, and then you'll just be ending up with whatever is this sort of inner function, and in this case that's what we want. So here we'll just end up with f of x times g of x on the left side because of the fundamental theorem of calculus, and on the right side we can actually split these up into two separate integrals, right, because we have this addition going on. So we can say that this is the integral of f prime of x times g of x dx plus the integral of f of x times g prime of x dx. Okay, so we're getting closer to what we want. We have actually two integrals here where you have a product of functions of x. It might look a little bit different to you though, because initially I said we had some function of x f of x times some function of x g of x, being integrated. Here, both of these contain a derivative, but that's fine. A derivative of x, a derivative of a function of x is still a function of x. And so this does actually match up with what we were looking for, and I'll show you why in a second. But why don't we try to get this function right here on one side? And we can do that simply by taking this function and moving it to the other side of our equation. I'm not going to write everything out because it'll take a long time showing all that subtraction. But what I will write is that the integral of f of x times g prime of x with respect to x is equal to this thing here, f of x times g of x, minus this integral here, right? Because I'm moving it to the other side. This is the integral of f prime of x times g of x with respect to x. This is the form that we had before. We had the integral of some function of x times some other function of x. I know that this is the derivative of x, but that is fine. That can work. And I'll show you exactly how with the example I gave you earlier where we had the integral of x times cosine of 5x dx. If we take x to be our f of x and cosine of 5x to be our g prime of x, we will be able to solve this integral, because if we find g of x, right, this is, if cosine of 5x is g prime of x, we know how to find g of x simply by integrating just cosine of 5x, which we know how to do. It's a single function. We know how to do that. And so we will be able to solve this using integration by parts. However, when you use integration by parts, you will not usually see it in the form I have written here. We usually write it in a little bit simpler notation. The notation we use is usually u dv. The integral u dv is equal to u times v minus the integral of, let's see here, v du. How do we come up with that? Well, if we say f of x is equal to u, right, then everywhere we see an f of x in our formula, we plug in a u. And if we say that g of x equals v, then every time we see a g of x, we plug in a v, right? Well, what about the du and dv? Well, let's look at that. If I took the derivative of both sides of this here, right, I would end up with, and it took the derivative with respect to x, I'd end up with f prime of x is equal to du dx. Okay, if I multiply both sides of this equation by dx, then I see that du is simply f prime of x dx. Okay, let's look at this one here. If I took the derivative of both sides of this equation with respect to x, I see that g prime of x is equal to dv dx. Moving the dx to the other side, I see that dv is just equal to g prime of x dx. All right, so originally I had, I'm just going to rewrite it here. Originally I had f of x times g prime of x. This is the integration by parts formula, but kind of a messier notation, or more complex notation, if you will. And this was equaling, one more try here, f of x g of x minus the integral of f prime of x times g of x. Let me fix my color here. G of x dx. Okay, let's look just on the left side. F of x. Well, that is u, right? We said f of x is u. G prime of x dx. G prime of x dx right here. That's dv. Okay, f of x we said is u. G of x, I said that's v. Minus the integral of f prime of x. Well, f prime of x by itself isn't anything, but f prime of x and dx together we said is du. So we have du out here. And then finally we see that g of x we said is equal to v. So we just say v. And that's how we come up with the sort of characteristic integration by parts formula that you're going to be seeing and using quite a bit. And so in the next video, I'm going to show how to apply this, excuse me, to solve the integral x cosine of 5x dx.